Good morning. Today we are going to discuss about the second reaction of organometallic complexes, which is oxidative addition and reductive eliminations. Okay, so the oxidative addition reaction is the most important, one of the most important class of reactions in organometallic chemistry, and this oxidative addition reaction can be understood by these examples. Okay, by taking one organometallic complex. So let's suppose we have an organometallic complex MLX, where M represents the metal and L represent the organic ligands. Okay, and X represent the number of ligands. Okay, so since we are talking about organometallic reactions, so we need an organometallic complex. So let's suppose this is our organometallic complex. Okay, having this M, that is the organo, that is your metal, and this is your ligand. Okay, so now for oxidative addition reactions, they are the organometallic complex must have some properties, or the organometallic compounds must follow some rules. Okay, to show the oxidative addition reactions. So the first rule, or you can say the first point, which should be there in that organometallic complex, is the metal which is present in that organometallic complex must have some vacant site. That means it should be coordinatively unsaturated complex. So that means must have vacant site means it is coordinatively unsaturated complex. Okay, understand? And the second point is that the oxidation state of the metal must be low. So these two conditions must be satisfied by that metal, then only those type of organometallic complexes can show oxidative addition reactions. Okay, so now suppose this complex is going to show your oxidative reaction, addition reaction. So what about that reaction? What will going to happen when the reaction will going to occur? Okay, so in oxidative reactions, usually two ligand, that means the number of the ligand should be two. Okay, the two ligand will going to uh, going to form bond with that metal. That means the metal must have two vacant site. Understand? So the metal will going to form bond with the two ligands, but at that time, okay, simultaneously when the metal will going to form the bond with the two ligand, then the formal oxidation state of the metal will going to increase by 2 unit. Why? Because it will going to lose two electrons when they will going to form the two bonds with that ligand na? Then that to form that ligand, it will going to actually the metal will going to lose two electrons, okay, during that process, that oxidative addition process. So we're going to discuss this process in details in first we have to understand what is this reaction. Okay, so in this reactions, actually two ligands will going to form bond with the metal, and during that formation of the two bonds, the metal will going to lose two electrons, and resulting the increment of the oxidation, formal oxidation of the metal by 2 units. Okay, so this is your the oxidative addition reactions. Understand? So the definition of this the oxidative addition reaction is given in your book, uh, and it is written like this: the oxidative addition reaction is a reaction in which a coordinatively unsaturated complex in a relatively low oxidation state undergoes a formal oxidation, okay, this is formal oxidation by 2 units, that is the loss of 2 electrons, and at the same time the increases its coordination number, that means number of bone, okay, by 2. Understand? So hope you understand the definition of the oxidative addition reactions. Now we're going to discuss about the some examples of oxidative addition reactions. Okay. So coming to the example of oxidative addition reactions, a well-known example of oxidative addition reaction which is shown by the Vaska's complex. Okay, so the Vaska's complex is actually a complex of iridium metal, and this iridium metal is coordinated by 4 ligands. That means the coordination number of this complex, that is 4, and here the 2 ligand L is actually triphenyl phosphine. Okay, 2 triphenyl phosphines are there and they are trans to each other. Okay, so the name of this square planar complex is actually trans carbonyl chloro bis triphenyl phosphine iridium 1. Okay, so that means the oxidation number of the iridium is 1. Okay, so when this actually this iridium, so first of all we have to check whether this this organometallic complex will going to show the oxidative addition reaction or not. So we know that to show or to exhibit the oxidative addition reaction, the organometallic complex must shows some or must follow some rule. It must follow. Okay, and the first one is that the metal must have some vacant sites. Okay, so if you see if you calculate its electronic configuration, then you will found that there will be some vacant site remain in that organometallic complex. Okay, and the second point is that the oxidation state of the metal must be low. Okay, so here you see the oxidation state of the iridium metal in this complex is only +1. So that means this complex, okay, that means this organometallic complex obeyed that 2 rules. Okay, then that means this there is a possibility of that means this complex can have show or exhibit the oxidative addition reaction. Okay, understand? So this is one example of a complex which have the capacity to show oxidative addition reaction. Okay, so let us now consider the reaction. Okay, how they will going to react to it is some different type of ligands. Okay, let's suppose this is your reaction. Okay, so this, let's suppose this Ml4 represent, actually M is actually your iridium. Okay, and L4 is actually one carbonyl and one chloride and one that means the other 2 are your triphenyl phosphine. Okay, suppose this is your Vaska's complex. Okay, so and this Vaska's complex, that means this 4 coordinated complex will going to react with 2 that means some react the 2 ligands actually. Okay, so it will going to react with some molecules. Okay, let's suppose this is hydrogen, so same thing. Okay, hydrogen, it can react with hydrogen or it can even react with oxygen also. Okay, so it may be anything. Okay, XY may be anything, it may be hydrogen, it may be oxygen or anything. Okay, so first of all what will going to happen, because it has that capacity to exhibit the oxidative addition reaction, so the metal can, this metal will going to react with this one and they will going to form two form bonds with the X and Y. Okay, that means the coordination number will going to increase by 2. Okay, and simultaneously, that means when the bond will going to form, then the oxidation state of the metal will going to also increase by 2. That means it will going to lose 2 electrons. Okay, so let's suppose, and here if we consider that Ml4 is your Vaska's complex, then we know that the oxidation state is +1. Okay, oxidation number, actually oxidation number of that metal is +1. Okay, so after the oxidative addition, the oxidation number of the metal will become 3 plus or +3. Okay, so you can say also +3. Understand? So again, one more important thing is that the reverse of this reaction, that means if these two ligand will going to you know that means if these two bond will going to break, that okay, then what will going to happen? If these two bond will going to break, then it will this complex will form Ml4 and the XY, and this reverse reaction is actually known as reductive eliminations, because here reduction is going to occur. You see, from +3 to +1, this process is reduction process. Okay, so reductive, and elimination process, because two group will going to be eliminated from that this complex. Okay, understand? So this is oxidative addition. Why oxidative addition? Because here the addition of two new group will going to occur, and oxidative. Why oxidative? Because the oxidation number of the complex is going to increase from 1 to +3, that means by 2 number. Okay, understand? So this is the example of oxidative addition reaction. Okay, before going to the discussion of the reaction mechanisms, we will going to focus on some important point, okay, of oxidative addition reactions. So mainly we have the idea about the oxidative addition reaction, that the oxidative to occur the oxidative addition reactions, there should be vacant coordination site must be available, okay, in the metal, and a 6 coordinated complex is not a good coordinate good candidate actually. So let's suppose a 6 coordinated complex. So this is your 6 coordinated complex. Let's suppose this is, okay, this is your 6 coordinate complex. So here actually they are already crowded. Okay, the ligands are in the 6 coordinated side now. So this is your x, this is your y. Suppose this is your y axis, this is x axis, and this is your z axis. Okay, excuse me. So that means they already occupied the all axis, and since they have some size now, the ligand occupies some volume in that space, so they have already occupied this space. Okay, so if we again further try to add some ligands from actually 2 ligands to that metal, then it will be not good for the stability of that metal or that organometallic complex, because it will going to because the 8-membered that means the 8-membered complex will going to experience more steric hindrance, that means more steric repulsions between the ligands, which causes the the complex unstable, that means which will going to make the complex unstable. Okay, so that means a 6 coordinated complex is not a good candidate, okay, for the oxidative addition reactions. Okay, but but it is possible, okay, but it is possible to that the 6 coordinate complex maybe they can exhibit the oxidative addition reactions. But the thing is that before before going to exhibit this or exhibit this oxidative addition reaction, the 6 coordinated complex must lose this, it must lose some ligands during the course of the reaction. That means before going to exhibit this oxidative addition reaction by the 6 coordinated complex, the 6 coordinate complex must lose some ligands. Okay, maybe 2, maybe 3. Okay, then it is possible to for them to exhibit the oxidative addition reactions. Okay, so this is an important point. And now the third point is also very important, which is the availability of suitable orbitals for bone formations. Okay, here it is written what? Suitable orbitals. So what is the meaning of suitable orbitals? So we know that from the concept of molecular orbital theory. So to form a bond, that means the bonds which are formed due to the contributions from bonding molecular orbitals is strong. That means if some bond will going to form between two atomic orbitals, okay, so if the two electrons from which are contributed from the two ligands or two two atomic orbitals, if the two if the electrons will be at the bonding molecular orbital, then that bond is your strong bond. Understand? So I'm again going to repeat this point. We know that if some molecule or some atom will going to form a molecule, then the atomic orbital will going to overlap. Okay, and by overlapping they will going to form what? Bonding molecular orbital and anti-bonding molecular orbitals. Okay, so let's suppose there are total 3. Okay, so if if the electrons of that atomic orbitals of the participating atoms will going to be only at that bonding molecular orbital, then that bonds will be your strong bond. Okay, if the bonding is due to the due to the this electron, let's suppose the electrons will be in that anti-bonding molecular orbitals, then that bond will be not your good bond, or that the strength of that bond will be not that bond will be not a strong bond. Understand? This bond will be your weak bond if some electron will be in the anti-bonding molecular orbitals. So this concept will going to be actually used in this availability of suitable orbitals for bond formations. Okay, so we can understand this point by using one example. Okay, so let us use an example of iron organometallic complex. Okay, let's suppose FeCO4, but here, so here 2 negative. Okay, so that means the oxidation state of this iron will be 2 negative. Okay, understand? So if you will going to calculate the number of electrons for this complex, then you will going to find 18 electron. Okay, that means 18 electrons. So it has, that means this complex has 18 electrons on the outermost orbitals. Okay, so that means this complex is already stable complex. Okay, so if you try to, but here you see the number of ligand present in this complex is 4. That means there is a possibility. Okay, according to the first rule, we can add two ligands in this complex to get the oxidative addition reaction. Okay, but here it is very difficult to add these two ligand in this complex. The reason behind is that the all molecular orbital is already filled by the 18 electrons. Okay, so the remaining orbitals are actually the antibonding molecular orbitals. Okay, so that means if by chance, if let's suppose this ligand will have can actually, let's suppose this ligand can form bond with this complex, okay, with this iron, okay, so that bond will be between the anti-bonding molecular orbital of this iron and the ligand orbitals, okay, so which is going to lead the which is going to lead a weak bond, or it will be not a stable complex, okay, so it will not going to give a stable complex. So that's why we have to check whether the molecular orbitals are, is there any vacant molecular orbitals are present or not, okay, so that means this is also a example of actually vacant coordinate site. Actually coordinate site is not vacant, coordinate site is there na, because it is 4 only, the coordination number is 4, okay, so vacant coordinate site is there, but the vacant molecular orbitals are not present here, okay, only antibonding molecular orbitals are present. So that's why this point is important, okay, so additionally, that means with the vacant coordinate site and the low oxidation state, we have to also one more point, that is the availability of suitable orbitals for bone formation, okay, so this is a very interesting point, okay, so please try to understand this point. So now we can go to that mechanism part, that means the reaction mechanism which is going to occur, or the most probable mechanism for that oxidative addition reactions, okay.